Modern knives dull with use. Sharpening requires equipment, skill, or professional services. The edge degrades until the knife becomes useless. Medieval scythes, farming tools, cutting grass for hours daily, were forged from steel that grew sharper as it was used. The blade's edge, hammered cold into work-hardened crystalline structure, regenerated its sharpness through the cutting process itself. This is the story of a metallurgical technology so sophisticated that modern materials science struggles to explain how illiterate blacksmiths created self-maintaining cutting edges and why every blade you own is designed to dull. Chapter 1. The edge that dies in weeks. Pull a kitchen knife from your drawer, one you've used regularly for 6 months. Try slicing a tomato. The blade crushes before cutting. The edge has rolled, dulled, microscopic damage accumulating with each use until the geometry that once sliced effortlessly now merely compresses. This degradation is inevitable in modern knives. The steel, typically stainless alloy, hardened to 56 to 58 HRC, begins sharp but cannot maintain that sharpness. Each cutting stroke generates microscopic edge damage. Steel at the apex folds over, creating a burr. The burr breaks off, leaving the edge thicker and duller. The cycle repeats until the knife requires resharpening. Most people sharpen knives every 2 to 4 weeks with heavy use. Many never sharpen properly and simply replace knives when they become too dull. Typically every 1 to 3 years, depending on quality and usage. The knife industry depends on this cycle. If knives stayed sharp indefinitely, sales would collapse to replacement of lost or broken tools. The business model requires edges that dull, creating demand for sharpening services, replacement blades, or entirely new knives. Americans purchase 180 million kitchen knives annually. If those knives maintained edges for 5 years instead of 1, the industry would shrink by 80%. Planned obsolescence isn't conspiracy, it's built into the material properties. Modern knife steel is optimized for initial sharpness and corrosion resistance, not edge retention. Meanwhile, in the Agricultural Museum in Schwäbisch Hall, Germany, a scythe blade from 1780 sits in working collection. The blade is 244 years old. Museum staff demonstrate it annually at harvest festivals, cutting grass for hours without resharpening. The edge remains functional because the blade's metallurgical structure, peened and work-hardened through techniques perfected over centuries, becomes sharper through use, rather than dulling. The cutting action itself maintains the edge geometry. Modern agricultural equipment manufacturers tried to replicate this property in the 1950 seconds and failed. The industrial steel, despite superior metallurgy and controlled manufacturing, could not match the self-sharpening characteristics of hand-forged scythe blades made by blacksmiths who couldn't read but understood steel at the molecular level through empirical mastery. Chapter 2. The iron that becomes steel. Medieval scythe blades began as wrought iron, nearly pure iron, with fibrous slag inclusions, produced in bloomery furnaces. This iron is soft, ductile, and unsuitable for cutting edges. Transforming it into steel required adding carbon achieved through forge welding, a high-carbon steel edge onto the softer iron body. The blacksmith heated wrought iron bar to welding temperature bright yellow, around 1,200 degrees Celsius. At this temperature, the surface becomes slightly molten, covered in fluid slag. A strip of high-carbon steel produced by prolonged heating of iron in charcoal was placed on this hot surface. The blacksmith hammered the two pieces together, forcing out slag and creating metallurgical bond at the molecular level. The hammer blows forged the materials into single piece, soft wrought iron forming the blade's body, hard steel forming the cutting edge. This composite structure was sophisticated engineering. The wrought iron body provided toughness and flexibility essential for a blade that might encounter rocks or hard earth. If the entire blade were hard steel, it would shatter under impact. The wrought iron absorbed shock, preventing fractures. But wrought iron cannot hold an edge. The high-carbon steel edge solved this. It could be hardened and sharpened to maintain cutting geometry. The blade combined contradictory properties, toughness and hardness, through material composition. Modern metallurgists call this edge packing, or laminated steel construction. It's used in premium Japanese kitchen knives, Viking swords, and high-performance tools. We treat it as advanced technique requiring precise control and modern understanding. Medieval blacksmiths used it as standard practice, judging by eye and experience when the weld was proper, when carbon content was sufficient, when the composite blade had correct properties. The Technical University of Aachen analyzed medieval scythe blades using electron microscopy, examining the iron-steel interface. The weld zones showed complete metallurgical bonding, no gaps, no inclusions, just gradual transition from low-carbon iron to high-carbon steel. The bonds were stronger than either material individually. Blacksmiths working without temperature measurement or material testing had created perfect forge welds through tactile and visual feedback refined across thousands of repetitions. Chapter 3. The hammer that changes structure. After forging the composite blade, medieval blacksmiths performed a crucial process, peening the edge. This cold working technique transformed the steel's crystalline structure, creating properties that modern materials science is only now beginning to understand. Peening involves hammering the blade's edge, while cold below the temperature where steel's crystal structure can reorganize. The blade was placed on an anvil, edge facing up. A narrow-faced hammer struck the edge repeatedly, delivering controlled blows that compressed and spread the steel. This created several effects. First, the hammering compressed the crystalline structure, creating residual stress in the edge. The steel's grain structure became progressively finer, with each blow large crystals fractured into smaller ones, creating denser, tougher material. Second, the peening work-hardened the steel. Steel's atoms can move and reorganize when heated. At room temperature, their mobility is limited. Hammering forces atoms into new positions where they remain locked, creating internal stress that resists deformation. The edge became harder than the bulk of the blade. Third, and most remarkably, the peening created gradient structure, hardness and stress, varying continuously from the edge apex, maximum hardness, to the blade, body, softer, more ductile steel. This gradient was invisible but critical to the blade's self-sharpening property. The technique was called sharp peening, or edge hardening in English, Dengeln in German. It was performed regularly. Scythe users would peen their blades every few hours of cutting, maintaining the edge structure through continuous work hardening. The process required skill. Too little hammering, and the edge wasn't adequately hardened. Too much, and the edge became brittle, chipping during use. The blacksmith or farmer had to judge the correct amount by sound the ring of hammer on steel and by feel the resistance of the steel to deformation. This tacit knowledge took years to develop. Modern materials scientists studying medieval blades discovered something unexpected. The peened edges showed nanoscale grain structure crystals, just 50 to 200 nanometers in diameter. This is nanostructured steel, produced through mechanical processing without any advanced technology. The fine grain structure provided extraordinary hardness and wear resistance. Attempts to reproduce this in laboratory settings, using modern hammering equipment, have achieved partial success. But the historical blades still show superior properties. The medieval blacksmith's empirical technique, refined across generations, optimized parameters that researchers are still trying to fully understand. Chapter 4. The geometry that cuts forever. The self-sharpening property of scythe blades comes from specific edge geometry created through peening. Unlike modern knives with symmetric V-shaped edges, scythe blades have asymmetric convex edges with compound angles, a geometry that interacts with wear in counterintuitive ways. The edge is ground from one side only, the blade's underside is flat, while the top surface curves down to the edge at a shallow angle, typically 12 to 15 degrees. This creates an edge that's essentially a chisel grind all the bevel on one side. But the peening adds complexity. The cold hammering creates slight convexity to the bevel instead of a flat plane. The surface curves gradually from thick to thin. This convex geometry means the edge apex contacts the cutting material at a very acute angle, while substantial steel mass supports just behind the edge. When the blade cuts grass or grain, the edge encounters resistance. The cutting material presses against the edge, creating compression stress. This stress concentrates at the edge apex, the thinnest, most vulnerable point. In normal steel, this would cause the edge to fold over or chip. In work-hardened peened steel, something different happens. The compression stress at the edge interacts with the residual stress from peening. The edge is already under internal compression from hammering. External cutting forces add to this compression. The combination creates stress state that encourages microscopic fracture of the edge apex. Tiny fragments of steel break away. This sounds like dulling, but it's actually controlled microchipping. The fragments that break away are the worn, slightly dulled portions of the edge. Behind them, fresh steel with intact crystalline structure is exposed. This fresh steel is slightly harder than the removed material. The work-hardening gradient means hardness increases with depth from the apex. The blade effectively sheds its worn surface, revealing sharper steel underneath. The process is self-regulating. As the edge wears slightly, it becomes marginally duller, increasing cutting resistance. The increased resistance generates higher stress, triggering microchipping that removes the dull layer. The blade maintains consistent sharpness through automatic material removal at the microscopic scale. Research at the Swiss Federal Institute of Technology measured this phenomenon using atomic force microscopy on scythe blades before and after extended use. They documented that the edge apex continuously renewed through the loss of 2 to 3 micrometer layers while maintaining consistent edge geometry. The blade was sharpening itself through controlled structural failure at the nanometer scale. Chapter 5. The stone that wakes the edge. Medieval scythe users carried whetstones, natural sandstone or novaculite to hone the edge during work. This wasn't sharpening in the modern sense, but rather maintenance of the self-sharpening structure. The stone, moistened with water, was drawn along the edge with light pressure. This removed any burr or folded metal, cleaned grass, sap, and debris from the edge, and potentially triggered the microchipping process that exposed fresh steel. The honing took 30 to 60 seconds, every 20 to 30 minutes of cutting. This frequent light maintenance was more effective than infrequent heavy sharpening. The blade never got dull enough to require significant material removal. It was maintained in continuously sharp state through minimal intervention. The stones themselves were specific materials. In Austria and Germany, Wasserstein waterstones from particular quarries were preferred. These were fine-grained sandstones that cut steel slowly and left smooth finish. In Britain, Welsh slates and Charnwood stones were traditional. Each stone type produced slightly different edge characteristics, and users had strong preferences based on local tradition and personal experience. Modern sharpening uses abrasive materials in sequence: coarse stones to reshape the edge, medium stones to refine, fine stones to polish. The process removes significant steel, creating entirely new edge geometry. This is necessary for modern knives because the steel cannot self-sharpen. It must be mechanically restored. Medieval scythe maintenance was different. The honing stone didn't reshape the edge, but cleaned and refreshed it, allowing the blade's inherent properties to maintain sharpness. The philosophical difference is profound. Modern sharpening imposes geometry on steel that cannot maintain itself. Medieval honing supported steel that maintained its own geometry. One approach treats the blade as passive material requiring external intervention. The other treats the blade as active material that self-regulates with minimal support. Chapter 6. The sound that teaches steel. Experienced scythe users and blacksmiths judged blade condition by sound. A properly peened blade, when tapped lightly, produced a clear, ringing tone, high-pitched and sustained. A blade needing peening produced duller sound, lower pitch, quickly dampened. This acoustic feedback revealed the blade's internal structure. The ringing sound comes from crystalline structure vibrating. Fine-grained, work-hardened steel with high internal stress produces clear, high-frequency vibrations. Coarse-grained, annealed steel with low internal stress produces muddy, low-frequency vibrations. The ear can detect differences the eye cannot see. Blacksmiths used this acoustic feedback while peening. They'd hammer the edge, tap it, listen. Hammer more, tap again, listen. The sound changed progressively as work hardening increased, rising in pitch, becoming clearer. When the sound reached the correct character memorized through years of experience, the peening was complete. This seems primitive compared to modern hardness testing using Rockwell or Vickers scales, but it provided real-time feedback during the peening process. Modern hardness tests require stopping work, preparing samples, measuring. Acoustic feedback is continuous and non-destructive. For process control in pre-industrial manufacturing, it was superior to any available alternative. Researchers at the Karlsruhe Institute of Technology investigated this phenomenon, correlating acoustic resonance with measured hardness and microstructure in historical scythe blades. They found strong correlation. Blades with higher pitched resonance consistently showed finer grain structure and higher hardness. The traditional acoustic assessment was detecting real material properties. Modern smiths working with traditional techniques report learning to hear the blade's condition. Initially, all blades sound similar. With practice, subtle differences become apparent. Eventually, the sound conveys detailed information, not just hard or soft, but hardness at the edge versus body, uniform or variable structure, proper peening or excessive hammering. The acoustic sensitivity is cultivated skill, similar to musicians' pitch discrimination. It can be learned, but requires extensive practice. Chapter 7. The Failure of Industrial Steel. In the early 1900s, industrial manufacturers attempted to mechanize scythe production. Steel could be produced in blast furnaces with precise composition. Blades could be stamped from sheet steel, ground to shape on powered wheels, and heat-treated in controlled furnaces. The result should have been superior, consistent material, precise geometry, optimized heat treatment. The industrial scythes failed. Farmers using them reported rapid dulling, edges that chipped easily, blades that required constant sharpening. The industrial products couldn't match hand-forged blades made by village blacksmiths using centuries-old techniques. The failure was instructive. Industrial steel was homogeneous, uniform composition and structure throughout. This seems advantageous, but it eliminated the composite structure that made traditional blades effective. The wrought iron body and steel edge, with their different properties, provided toughness and hardness where each was needed. Uniform steel was either too hard, brittle, or too soft, couldn't hold an edge. Heat treatment couldn't replicate peening's effects. Industrial blades were hardened by heating to critical temperature, quenching rapidly, then tempering. This created hard steel, but the hardness was uniform, and the structure was different from work-hardened steel. Heat-treated steel has martensitic structure, needle-like crystals providing hardness but also brittleness. Work-hardened steel has deformed ferrite and pearlite structures, not as hard but much tougher, with the gradient hardness that enabled self-sharpening. Most critically, industrial blades lacked the residual stress pattern from peening. The compression at the edge, created by cold hammering, was essential for the microchipping mechanism. Heat-treated steel had different internal stress distribution that didn't support self-sharpening. By the 1950 seconds, industrial scythe production had mostly ceased in Europe. Mechanical mowing equipment replaced hand scything for most applications. But in regions where scythes remained in use, alpine meadows, too steep for machinery, organic farms avoiding fossil fuel equipment, homesteaders and traditional farmers' demand for traditionally forged blades continued. Small forges in Austria and Germany maintained hand-forging production, supplying this niche market. These traditionally made blades commanded premium prices 5 to 10 times the cost of industrial blades, but performed so much better that serious users considered them essential. The inferior technology was more expensive, but superior in function. Industrial efficiency couldn't compete with craft mastery. Chapter 8. The economics of maintenance versus replacement. A traditionally forged scythe blade, properly maintained through regular peening, lasts 20 to 40 years of seasonal use. The blade might be honed thousands of times and peened hundreds of times, but retains functionality across decades. Replacement occurs when the blade becomes too narrow from material loss, or when structural damage makes it unsafe. Modern disposable blade designs, stamped steel scythes or rotary mower blades, last 1 to 3 seasons before requiring replacement. The blades dull quickly, cannot be effectively peened, and are designed as consumable components. The cost comparison is striking. A premium hand-forged Austrian scythe blade costs $60.90. Over 30 years, this is $2.03 per year of use. A modern industrial blade costs $15.25, but requires replacement every 2 to 3 years, totaling $150.375 over 30 years, or $5.12 per year. The expensive traditional blade is dramatically cheaper across its lifetime, but the costs are distributed differently. The traditional blade requires upfront investment, plus ongoing maintenance time, peening every few hours of use, honing every 20 to 30 minutes. The modern blade requires minimal maintenance, machine sharpening occasionally, but frequent replacement. For users with limited capital, the modern blade is accessible. $20 is manageable. $80 might not be. For users with limited time, modern blades require less skill and maintenance labor. The economic structure favors different choices for different circumstances. The traditional maintenance model requires initial investment in quality tool, skill development in maintenance techniques, time allocation for regular maintenance, and long-term thinking to realize life cycle cost savings. The modern replacement model requires minimal initial investment, no skill development, minimal maintenance time, and short-term thinking accepting higher lifetime costs. Our economy favors the replacement model. Consumer goods are designed for obsolescence. Skills training is increasingly rare. Time is valued over quality, and short-term thinking dominates. These factors push consumers toward inferior solutions that seem economical initially, but prove expensive over time. Chapter 9. The Master Who Forges. In Schornstein, Austria, a company called Sharpens continues producing hand-forged scythe blades, using techniques essentially unchanged since the 1600s. The workshop contains forges, anvils, and hammers that would be recognizable to medieval blacksmiths. The process begins with steel bar stock, modern steel, purchased from mills, with specified carbon content. This is concession to modernity. Historically, smiths produced their own steel through time-intensive carburization, but the forging process is traditional. The steel is heated in coke-fired forge to yellow heat, then drawn out under power hammer blows, stretching and thinning the material into blade shape. The tip is forged to delicate point, the heel formed with robust tang for handle attachment. The blade's curve, specific to scythe type and regional tradition, is created through careful hammer control. Once forged to rough shape, the blade is ground. This happens on large, slow-turning sandstone wheels, water-cooled to prevent overheating the steel. The grinder shapes the edge bevel, creates the blade's flat underside, and establishes precise thickness profile from spine to edge. Then comes hardening. The blade is heated uniformly to critical temperature, judged by color in darkened room and quenched in oil. This creates hard but brittle steel. Immediately after quenching, the blade is tempered, reheated to lower temperature that reduces hardness slightly while dramatically improving toughness. The temperature is judged by oxide colors forming on clean steel surface, straw yellow for maximum hardness, purple blue for balance of hardness and toughness. Finally, the edge is peened. This happens on specialized peening anvils, narrow, hardened steel forms that support the blade's curve. The smith strikes the edge with cross-peen hammer, working from heel to tip in overlapping blows. The edge gradually work-hardens, the steel ringing progressively higher in pitch. Experienced smiths complete this process in 5 to 10 minutes, producing edges that casual observers cannot distinguish but users immediately recognize as superior. The company produces roughly 10,000 blades annually, minuscule compared to industrial production, but sufficient to supply the global market for premium hand-forged scythes. They employ 12 smiths, most over 50 years old, all trained through multi-year apprenticeships. When current smiths retire, the company's future is uncertain. Younger people rarely apprentice. The work is physically demanding, the pay modest, the career prospects unclear. Chapter 10. The science that validates craft. Contemporary materials science has extensively analyzed traditional scythe blades, attempting to reverse engineer their properties and replicate them through modern processes. The research consistently validates traditional techniques while revealing complexity that challenges replication. Electron microscopy studies at Vienna University of Technology examined the edge structure of 18th and 19th century scythe blades. The peened edges showed extraordinary grain refinement crystals, averaging 100 to 200 nanometers in diameter at the apex, gradually increasing to 1 to 2 micrometers in the bulk steel. This gradient structure is nanostructured metal, produced through mechanical processing centuries before the term nanotechnology existed. Hardness mapping using nano-indentation revealed hardness gradients from 600 to 700 HV, Vickers hardness, at the edge to 400 to 500 HV in the blade body. This 50% hardness variation across millimeter-scale distances was created through peening. The cold work concentrated at the edge, while the blade body remained softer and tougher. Researchers attempted to replicate this using modern equipment, power hammers with controlled force, precision temperature control, and advanced steel alloys. The results were disappointing. Modern reproductions achieved grain refinement and hardness increase, but not the specific gradient structure or self-sharpening behavior of historical blades. Subtle differences in peening technique, hammer face geometry, impact energy, working temperature, number of passes created dramatic differences in final properties. The traditional technique had been optimized through countless iterations by generations of smiths. Modern researchers, working with limited time and attempts, couldn't match the empirical optimization. The most significant finding was the importance of the iron-steel composite structure. Blades forged entirely from modern alloy steel performed worse than traditional blades with wrought iron bodies and steel edges. The composite structure provided mechanical properties that homogeneous steel couldn't achieve. The tough, fibrous, wrought iron absorbed impact stress, protecting the hard but brittle edge steel. Current research explores applying these principles to modern tool steels. Some premium Japanese knife makers use laminated construction, explicitly inspired by historical European agricultural blades. The recognition is growing that pre-industrial metalworking achieved sophistication through empirical method, that modern theory-driven approach struggles to replicate. Chapter 11. The technique that travels. Scythe forging techniques weren't uniform across medieval Europe. Regional variations existed, each adapted to local materials, agricultural requirements, and craft traditions. Austrian blades were renowned for long, thin, highly curved designs suited to mountain meadows. German blades were shorter and more robust, designed for grain harvesting. English blades were heavy and durable, used in orchards and hedging as much as grass cutting. These variations weren't arbitrary, they reflected deep understanding of how blade geometry, material properties, and use patterns interacted. The Austrian style, with its extreme curve and thin profile, required high-quality steel and expert peening. The blade was lightweight and cut effortlessly through grass, but was more fragile and demanded careful maintenance. The German style sacrificed some cutting ease for durability and versatility. The blade could handle rougher conditions, encountering rocks or thick stems without damage. The English style was almost a different tool, thicker, heavier, designed for chopping as much as slicing. Despite these differences, certain principles were universal. Composite steel construction, edge peening for work hardening, asymmetric edge geometry, and regular maintenance through honing. These weren't regional variations, but fundamental techniques that emerged independently across Europe and beyond. The global spread of scything was often traced through blade types. The Austrian style spread through Germanic regions into Eastern Europe and eventually to North America with immigrants. Where Austrian-style blades appeared, you could trace migration patterns and cultural transmission. This created interesting hybrid traditions. In Pennsylvania, where German and English settlers mixed, blade styles blended, combining English durability with German geometry and Austrian peening techniques. In New Zealand, European settlers adapted traditional blades to native grasses with different cutting properties, modifying edge angles and peening patterns through local experimentation. The techniques weren't static tradition, they were living practices that adapted to new conditions while maintaining core principles. This adaptability is characteristic of craft knowledge. Unlike engineering specifications, which are rigid and context-specific, craft techniques are flexible frameworks that practitioners adjust based on materials, conditions, and needs. Chapter 12. The Conservation Dilemma. Museums holding historical scythe blades face unique conservation challenges. The blades are tools, designed for use, and much of their significance lies in functional properties that cannot be displayed. A scythe blade in a case looks like a curved piece of steel. Its self-sharpening edge structure, gradient hardness, composite materials, none of this is visible. To truly understand the blade, you must use it. But use causes wear, potentially damaging irreplaceable artifacts. Some museums have addressed this through replication. They commission traditionally forged blades from remaining master smiths, creating working duplicates that can be demonstrated while preserving originals. This allows educational programming, showing visitors how scythes were used, letting them feel the cutting action without endangering artifacts. Others take different approach, using advanced analysis techniques to document blades' properties in detail, then archiving this data. Future researchers can access metallurgical information, microscopy images, hardness maps, and compositional analysis without handling fragile objects. This preserves knowledge, even if artifacts deteriorate. But neither approach fully solves the problem. The replicas, however accurate, are new objects without the historical continuity of originals. The data, however detailed, cannot capture the tacit knowledge of how the blade feels in use, how the edge bites into grass, how the balance shifts as you swing, how the sound changes as the blade dulls. This experiential knowledge, fundamental to understanding the tool, resists documentation. Some conservators argue that limited, controlled use of historical tools for demonstration and teaching is appropriate, that the risk of minor wear is justified by preservation of knowledge. Others maintain that artifacts should never be used, that documentation and replication are sufficient. The debate reveals tension between preserving objects and preserving practices. A perfectly preserved blade that nobody knows how to use is historical object, but not living tradition. A worn blade accompanied by practitioners who maintain the craft is connection to continuous practice. The question is, which matters more? Chapter 13. The revival that's fragmenting. Small but growing communities are reviving traditional scything using hand tools for grass cutting instead of powered mowers. The motivations are diverse: environmental concerns about fossil fuel consumption, desire for quiet tools, physical exercise, connection to traditional practices, and practical requirements like steep terrain where mowers can't operate. This revival creates demand for traditionally forged blades and for instruction in their use. Scything associations in Europe and North America offer workshops teaching technique how to peen edges, maintain tools, and cut grass efficiently. These workshops attract participants from organic farmers to suburban homeowners to historical reenactors. The skill transmission happens through demonstration and practice exactly how traditional knowledge always transferred. But the revival is fragmentary and inconsistent. Many participants treat scything as hobby or occasional activity rather than regular practice. The skills don't develop to professional level because the time investment isn't there. A medieval farmer might spend hundreds of hours annually scything. Modern practitioners might accumulate 20 hours over several years. The depth of mastery is incomparable. The market for quality blades is growing but remains tiny. Perhaps 5,000 to 10,000 serious users exist globally enough to sustain the few remaining forge workshops, but not enough to attract new manufacturers or justify industrial investment. The craft survives in the narrow space between extinction and viability. Some participants become deeply committed, developing real skill and maintaining regular practice. A few apprentice with remaining master smiths, learning forging techniques. These individuals become knowledge carriers, potentially bridging to next generation. But they're exceptions. Most participants remain casual practitioners, and the knowledge they carry is incomplete. The question is whether this fragmentary revival can coalesce into stable tradition or whether it's temporary phenomenon that will fade as current practitioners age. The answer isn't predetermined, it depends on cultural factors beyond scything itself, on whether skill-based, low-technology solutions gain broader acceptance in society, concerned with sustainability and resilience. Chapter 14, The Regulation That Nobody Wrote. Interestingly, scythe blade forging has escaped most modern industrial regulation because it's artisan production in small workshops, not factory manufacturing. Standard metalworking regulations often don't apply. There are no required safety certifications, no mandated quality standards, no bureaucratic approval processes. This regulatory absence is double-edged. On one hand, it allows traditional smiths to continue working as they always have, without compliance costs that might make small-scale production economically impossible. They forge blades by eye and experience, without specifications or testing beyond their own quality judgment. On the other hand, it means consumers have no standardized way to evaluate quality. A blade advertised as traditionally hand-forged might be authentic product from master smith, or it might be industrial blade with hand-finished edge. No certification distinguishes them. The market relies on reputation, word of mouth, recommendations, reviews from experienced users, and the smith's track records. This was medieval quality control system, and it works within small, knowledgeable communities, but it doesn't scale. As scything revival brings more users with limited experience, the risk of low-quality products being marketed as traditional increases. Some users propose voluntary certification, scything associations or craft guilds establishing standards for what constitutes properly forged and peened blade, and certifying smiths who meet those standards. This would provide consumer protection while avoiding government regulation. Others argue that certification bureaucratizes craft, imposing formality that might exclude innovative techniques or emerging smiths. The tension between quality assurance and craft freedom is ongoing. Currently, the market is small enough and interconnected enough that reputation mechanisms work. If the market grows substantially, pressure for formal standards may increase. Whether that would help or harm the craft is debatable. Chapter 15, The Edge That Waits. You can buy traditionally forged scythe blade. Several Austrian and German smiths sell directly to international customers. The blade costs $60.90 plus shipping. It arrives unsharpened. You must peen the edge yourself or have it done by someone experienced. The technique is documented in videos and written guides. It requires a narrow anvil or peening jig, a cross-peen hammer, and patience to learn the rhythm and sound of proper peening. Most users take months to develop competence and years to achieve real skill. This barrier, the learning curve, is feature, not bug. Tools that require skill to maintain create relationship between user and object. You cannot be passive consumer of disposable products. You must engage with the tool, learn its properties, develop capability. This engagement creates appreciation and care that disposable products never inspire. The alternative is powered equipment, string trimmers, rotary mowers, brush cutters. These require minimal skill, work quickly, and demand little maintenance beyond fuel and occasional blade replacement. They're more convenient in every measurable way, except they're loud. They consume fossil fuels. They cannot be repaired by users. They dull quickly and require constant component replacement. They sever connection between user and the machine intermediates, making grass-cutting industrial process rather than craft practice. The scythe offers different relationship, quiet, human-powered, repairable, dependent on skill, connecting user directly to the work. You feel each stem cut, adjust technique to grass conditions, develop rhythm and efficiency through practice. The tool becomes extension of body in ways powered equipment never does. Medieval farmers using scythes daily for entire growing seasons developed extraordinary proficiency. They could cut grass faster than modern recreational users with string trimmers. The skill, developed through necessity and practice, made the simple tool astonishingly effective. That skill is accessible. The techniques are documented. The tools are available. What's required is commitment, choosing to develop capability rather than delegate work to machines, accepting the learning curve, valuing the craft. The edge that sharpens itself is still there, in workshops in Austrian valleys, in the hands of elderly smiths, in the muscle memory of users who learned from users who learned from users reaching back through generations. It's waiting, patient as steel, persistent as tradition, ready to teach anyone willing to learn that the most sophisticated technology isn't always the newest, and sometimes the tools that seem simplest contain the most profound engineering.